Before the dinosaurs existed, one animal had already been ruling the planet for 20 million years. Not a predator, not an apex carnivore, a herbivore, processing the most nutritionally worthless food on the planet, and doing it so efficiently that it became the most common large vertebrate on Earth. An animal with no claws, no fangs, no speed. And it dominated anyway. Think about what that means. The T-Rex, the animal that has defined our image of prehistoric dominance, lasted roughly 2 million years before extinction took it. This animal lasted 30 million. It outlasted the T-Rex by a factor of 15, and did it not by being the most dangerous thing in its world, but by being the most indispensable. This is the Edaphosaurus. And the question worth asking is not what it was, but what problem it solved. Because the Permian, the world it inherited, had handed every living thing a puzzle that almost nothing could crack. An endless supply of food that was essentially indigestible. The plant material of the early Permian was fibrous, silica-laced, and nutrient-poor to a degree that makes modern cellulose look like sugar. The Edaphosaurus didn't just eat it. It built an entire biological architecture around processing it, and by doing so, unlocked an energy source that nothing else could touch.
Forget the image of prehistoric Earth as a humid, fern-carpeted paradise. The Permian was a world of extremes. Temperatures at the equator that exceeded anything in recorded human history. Multi-year droughts that made the Sahara look manageable. Climate swings so radical that ecosystems that took millions of years to build could be dismantled in a single bad season. The Carboniferous, the era just before, had been defined by vast coal swamp forests, towering lycopsid trees stretching 20 meters or roughly 65 feet into the air, carpeting what is now North America and Europe in green. Then those forests collapsed. The Carboniferous rainforest collapse, one of the most catastrophic climate disruptions in pre-Permian history, fragmented and destroyed those ecosystems in a geological instant. Most of the animals living in them went with them.
The Edaphosaurus survived. It carried that resilience forward, out of the dying Carboniferous and into the hostile Permian, where it would thrive for tens of millions of years more. But to understand why it thrived, you need to understand the one resource the Permian had in unlimited supply, and the one biological problem that had never been solved at large scale. The Permian's environmental budget was brutal. Oxygen levels fluctuated in ways that placed hard limits on sustained activity. Water was seasonally scarce across vast interior regions. Prey animals, for a carnivore, were a finite and contested resource. You competed for them with every other predator in the ecosystem, and a failed hunt had real physiological consequences. But the plants were everywhere. Seed ferns, horsetails, club mosses, cordiatalian trees, an almost unlimited biomass covering every floodplain and delta margin in the landscape, and almost nothing could eat it efficiently. The silica content of many Permian plants functioned like microscopic glass embedded in every fiber. The cellulose ratios were extreme. The caloric return per gram of material was, by modern standards, catastrophically low. To extract meaningful energy from this food, an animal needed two things: a grinding apparatus capable of mechanically breaking down material that would shred conventional teeth, and a fermentation system, an internal chemical reactor capable of extracting nutrients from plant fiber that simple digestion cannot touch. Modern ruminants evolved this system. Modern horses evolved a version of it. Elephants refined it. But this animal had it first, by a margin of more than 250 million years. By being the only large vertebrate in the early Permian capable of efficiently processing this food,
The Edaphosaurus hadn't just found a niche, it had found a monopoly, an energy source of essentially unlimited supply with zero competition at scale. The entire ecosystem above it, the predators, the scavengers, the smaller animals feeding on its leavings, was built on the foundation of what it ate and processed and returned to the soil. It was not just an animal, it was an ecological engine.
At roughly 3.5 meters in length, about 11.5 feet, approximately the length of a mid-sized family car, the Edaphosaurus was not built for speed. It was built for throughput. A low, wide, heavily muscled torso housing a gut the size of a large oil drum, supported by a skeleton engineered for one thing: keeping that digestive system moving continuously for decades. The mass estimates run to approximately 300 kilograms, around 660 pounds, close to the weight of a large male grizzly bear, but distributed horizontally, close to the ground, with limbs splayed in the ancestral synapsid posture. This meant a low center of gravity and exceptional stability, at the direct cost of speed. The Edaphosaurus could not run from a predator. It was not designed to.
Which raises a problem. An animal that cannot flee, weighing as much as a grizzly, moving across open floodplains in a world stocked with large, well-adapted carnivores. How does it survive? The answer begins in the skull, but not where you'd expect. The Edaphosaurus had no fangs. The teeth it did have were peg-like, blunt, arranged in a mosaic pattern. And critically, they were not limited to the jaws. The palate itself, the roof of the mouth, was a second grinding surface. Two independent crushing plates working simultaneously on every mouthful of fibrous, silica-laden plant material. Paleontologists can identify Edaphosaurus fragments from millimeter-scale fragments of palatal bone alone. The architecture is that distinctive, that specific. This was not a generalist dentition. It was precision engineering, optimized over millions of years for one specific mechanical problem: reducing the most resistant plant material of the Permian to something a gut could chemically process. The biomechanics are closer to a millstone than a jaw, and what it was grinding and in what quantities is what made this animal a geological force.
Where the Edaphosaurus solved scarcity by turning worthless plants into energy, Tanystropheus solved the same survival problem in the opposite way. A 6-meter reptile with a neck longer than its body hunted from the shallows like a living spear. How did a dog-sized body wield a 3-meter javelin and survive for 37 million years? Tanystropheus' story picks up where this one leaves off. Like this video and subscribe to see it first. Now we arrive at the feature that has puzzled paleontologists for over a century, and the one that almost nobody has explained completely: the sail. It shouldn't exist. Every centimeter costs energy to build. Every gram increases visibility to predators. Every blood vessel requires maintenance. Natural selection is not sentimental. It eliminates costly features that don't earn their keep, in geological timeframes that are unforgiving. And yet, here is a structure rising up to 1.5 meters, nearly 5 feet above the animal's back, taller than the animal is wide, composed of dense, vascularized bone. The sail is formed by elongated neural spines, extensions of the vertebrae projecting upward from the back. These are not hollow. They are solid bone, richly supplied with blood vessels. And the Edaphosaurus sail carries something that no other sail-backed animal in the fossil record possesses: crossbars, horizontal projections on the spines, like the rungs of a ladder spaced along a radio tower, running perpendicular to the main spines at regular intervals. No other sail-backed animal has this, not before, not after. Which means the Edaphosaurus sail was not just elaborate,
It was uniquely elaborate. Something specific about this animal's life demanded a complexity that no other organism, across hundreds of millions of years of vertebrate evolution, ever required. 3 theories have emerged. The debate is not settled. And the most accurate answer is also the most structurally interesting. The first theory is the intuitive one. The sail was a solar panel. A large, flat, blood vessel-rich surface, oriented perpendicular to the early morning sun, could theoretically raise the animal's core body temperature by several degrees Celsius, several degrees Fahrenheit, in under an hour. In practical terms, this means the Edaphosaurus could be mobile, alert, and actively feeding at dawn, while cold-blooded competitors were still physiologically incapable of sustained movement.
The bone histology supports this. Cross-sections of the sail spines show vascular networks consistent with high blood flow, exactly the pattern you'd expect in a structure engineered for rapid heat exchange. But here is where the theory becomes insufficient. If thermoregulation was the primary function, the crossbars make no sense. A heat exchange fin does not need horizontal projections. They add structural complexity, they add weight, they add construction cost, and a radiator doesn't require them. The anatomy is telling us the thermoregulation theory is incomplete. The second theory, the sail was a biological billboard, a display structure used in mate selection, territorial signaling, or species recognition.
This is not a fringe idea. The logic of honest signaling is well established. A structure this expensive to grow and maintain can only be supported by a genuinely healthy, well-nourished individual. It is an advertisement of biological quality, written in bone that cannot be faked. Long before the peacock's tail, before antlers, before the elaborate displays of any mammal or bird, the Edaphosaurus was potentially running this same evolutionary calculation. The problem is that the fossil record doesn't give us a clean dimorphic signal. In most display structure species, deer, elk, many birds, dominant individuals carry substantially larger structures than subordinates or opposite sexes. In Edaphosaurus, individuals of apparently similar age show similar sail proportions. That doesn't disprove display, but it does mean the display theory alone is also incomplete.
The third theory is the one that has gained the most traction in recent decades, and the one that almost never makes it into the museum exhibit. Consider the crossbars again, but now consider them under load. When researchers modeled bite force stress patterns on the Edaphosaurus sail, they found something that changes the interpretation of the entire structure. The crossbar configuration dissipates compressive load laterally along the spine in a way that a simple vertical neural spine cannot. Under simulated attack conditions, the structure behaves like an engineered impact absorber. A predator biting down on the animal's back encounters not a simple spine that bends and breaks, but a lateral load distribution system that resists penetration and redirects force away from the spinal cord.
This is not a radiator. It is not a billboard. It is closer to spinal armor. And the most complete answer, as with most complex biological structures, is that the sail performed all 3 functions simultaneously. Thermoregulatory advantage at dawn, display signal at close range, structural defense under predator attack. Natural selection is not an engineer who designs for one purpose. It is an opportunist that exploits every advantage a structure provides. The Edaphosaurus sail is not a mystery with a single answer. It is a masterclass in biological multitasking, built once, paid for many times over telling.
The early Permian was not just a harsh physical environment. It was a world of specialists locked in evolutionary arms races that had been running for millions of years. And into this landscape, the Edaphosaurus walked everywhere. Fossil records indicate it was among the most common large vertebrates of the early Permian in North America, found from what is now Texas to New Mexico to Oklahoma, across the ancient floodplains and delta margins of the equatorial supercontinent. Not a rare apex predator, not a cryptic ambush animal, a biological constant. 3.5 meters and 300 kilograms of mobile ecosystem processing, visible from a considerable distance, moving slowly, eating continuously, which means it was a target. Allow me to correct something. When most people picture a sail-backed prehistoric animal, they picture the Dimetrodon, and they picture it as a dinosaur, or at least as something in the same general category as a dinosaur.
Both assumptions are wrong, and the truth is more interesting than the myth. Dimetrodon was not a dinosaur. It was not even a reptile in the modern sense. If you drew a family tree connecting every living lizard to every living human being, Dimetrodon would sit closer to your branch than to theirs. It is classified as a synapsid, part of the lineage that eventually produced mammals. When you look at a Dimetrodon skull, you are looking, in a very real biological sense, at a distant portrait of your own ancestry. And the Edaphosaurus? Also a synapsid. Also therefore closer to you than to any living lizard. These two animals shared the same landscape, the same geological period, the same body plan at a glance. But their ecological roles were as different as a wolf and a bison. The Dimetrodon was equipped with differentiated teeth. The name literally means 2 measures of teeth, capable of gripping, tearing, and processing prey. Its skull shows the musculature of an active hunter.
Its fossil record shows something more direct. Edaphosaurus bones bearing Dimetrodon tooth impressions in permanent geological record that confirm these two animals were not merely neighbors. They were locked in one of the longest-running predator-prey relationships of the early Permian. The Edaphosaurus, at an estimated 300 kilograms, 660 pounds, was very much on the menu. And yet, the Edaphosaurus survived. For 30 million years, 10 times the entire span of human existence on this planet, from the first stone tools to this present moment, it survived. Through predation pressure, through climate instability, through competition from successive waves of new carnivore designs, it endured. The answer is not complex. An animal that controls an unlimited food source and becomes the foundational caloric link in an entire ecosystem does not need to outrun its predators. It needs to be too important to eliminate. The Edaphosaurus was so deeply embedded in the function of its environment, cycling nutrients, building soil, sustaining the predator tier above it, that the ecosystem itself had an interest in its persistence.
Nature does not always protect the strongest. It protects the necessary. Approximately 252 million years ago, something happened that the Earth had never experienced before and has not experienced since. A flood basalt province in what is now Siberia, the Siberian Traps, covering roughly 5 million square kilometers, or about 1.9 million square miles, an area larger than the entire European Union, began erupting continuously. Not for a year, not for a century, for perhaps a million years. The carbon dioxide released did not change atmospheric chemistry in parts per million. It restructured it. The result was the Permian-Triassic extinction event, known among paleontologists with grim understatement as the Great Dying. Approximately 96% of all marine species gone. Approximately 70% of all terrestrial vertebrate species gone. The fossil record from the boundary layer makes the scale visible to the naked eye. Below the line, diversity. Above the line, almost nothing. A geological full stop written in rock. The Edaphosaurus does not survive the Great Dying. Its genus disappears from the fossil record in the late Permian, possibly before the main extinction pulse, possibly caught in its leading edge. The precise moment of its last individual is not recoverable from stone. An animal that had outlasted every predator, every climate swing, every ecological disruption of the early Permian. Undone not by a superior competitor, not by a more efficient design, but by the chemistry of its own atmosphere, changing faster than any biological system could track.
The Permian-Triassic extinction was driven primarily by the rapid, large-scale injection of carbon dioxide into the atmosphere, carbon that had been locked underground for hundreds of millions of years, released by volcanic activity over the course of roughly 1 million years. The consequences were ocean acidification, global temperature rise, and the collapse of ecosystems that had taken eons to build. The Siberian traps took approximately 1 million years to release their full carbon load. Current estimates place our rate of atmospheric carbon injection at roughly the equivalent of 1 Siberian traps eruption every 2 to 3 years. The situations are not identical. The organisms are different. The continents were different. The feedback loops were different. But the underlying mechanism, carbon sequestered underground for hundreds of millions of years, suddenly and rapidly returned to the atmosphere, is similar enough that paleoclimatologists use the Permian-Triassic boundary as one of the closest available natural experiments for understanding rapid greenhouse warming. Not as a perfect analogy, as a data point, a precedent, the closest thing geology offers to a before and after. The Edaphosaurus ruled this planet for 30 million years. It survived the collapse of the Carboniferous forests. It survived the predation pressure of the Dimetrodon. It survived climate swings that would have erased most modern ecosystems entirely. It was, by any reasonable measure, one of the most durable large vertebrates this planet has ever produced. It could not survive a change in atmospheric chemistry. Here is what paleontology gives us that the fossil record alone cannot: proportion. The ability to zoom out far enough to see not just the ending, but the scale of what was lost, and the mechanism that lost it. The Edaphosaurus didn't fail. It was perfectly suited to its world. The world simply stopped being its world, faster than evolution could answer.
Somewhere beneath Texas, Oklahoma, and New Mexico, the bones of millions of Edaphosaurs still lie in ancient river sediment, waiting. They ruled their world for 30 million years. Without those bones, we would never know they existed at all. Which means the question worth sitting with is not what killed the Edaphosaurus. It's how many 30 million year success stories are still down there, in rock we haven't broken open yet, that we will never know existed. The most durable things that ever lived may already be forgotten, and we are not yet old enough to know which category we belong to.